Come on then, let's make a start. Sorry about today, I had to do something. You saw me go past you downstairs. Part of the pain of working with me. Something always comes up. Okay, so Darren's collecting feedback. Just a quick thing on the employability on the event that we had for careers. Some of the feedback he's got from some of the students is less than, how can one put it, helpful. Saying things like, why was it open to the first years? Might not be you lot, of course, but why was it open to the first years? Because we want first years to go on placements, we want them to have an advantage that you didn't have. So that's why we got them over to this thing. Some of you said there weren't enough employers there. I expected more employers because you can't fit any more employers in, and we deliberately kept it small and bespoke to engineering. I can say those were the negative comments, and that was it. There were a couple of things like other small things about, oh, it would be good to have. But what I want to tell you is more importantly the feedback they had on you. The feedback they had on you was pretty much all well prepared that came to see them. Some were a little nervous on first approaches, but pretty good. Preparation is great, not always been true at big events. We met people we didn't know. We had a good tour of the pilot plant, or the James Trevor building, and we got to feel the environment that the students you graduate are working in. So from the employabilities, from the people, the employers themselves, they felt the event was brilliant, almost to a company. So there were 15 companies there, and every one of them fed back really positive things. Also, more importantly, they fed very positive things about you, which I think is important, since you may not have gone to that event. But if you did go to that event, they thought you were well prepared, they thought you knew where you wanted to go, you had some insightful questions, and for the Bechtel people in particular, they were delighted because some of our students, Tim Adams is one of them, because I spoke to him because he happens to be my tutee in industry and also my tutee for stuff, and he said, oh, I'd never heard of them, I didn't know who they were, and Bechtel were extremely pleased because they had, literally, they said they were inundated with people, so they were very pleased. So from a company's point of view, who's not very well known, they were thrilled to bits. So remember, the event's a two-way street, and we are going to try and get another event for for third, fourth years, second years, maybe first years as well, just to keep it rolling because we've never done it before. So thanks for those that have fed comments back. If anybody else still wants to feed comments back, Darren will still receive them. And if they're a little bit more constructive than saying why did the first years attend, then that would be helpful. But if you want to feedback also you didn't like it, then fine. But don't expect 1,000 employers turning up. We're not GMEX and we're not organising a massive conference. We're just organising a bespoke one for 10 But thanks for your feedback. Darren wanted to flag that. And also I thought it was very important to know what the employers thought of you. First impressions. First impressions count a lot, remember. So I think that's really good. So enough on that. To work. So remember this afternoon it's a lecture at 2 till 3 and we're in here. Yeah? We've got, I think, probably 3 more weeks and we've got 3 more lectures in Reynolds because you're probably thinking, oh, we're only halfway through the booklet or we're not far enough on. We're exactly where we should be. I pointed out the Langley or Hinchelwood and we're just going to cover the Thiele modulus today. And tomorrow, maybe this afternoon, depending on timing, we'll get to some new reactor systems that you've not seen before, although you can have seen one of them anyway. But we'll introduce that and some extra kinetics. And then the next 2 weeks, we'll talk about catalysts themselves. Now, the 2 gentlemen who I picked on at the front, why are we talking about effectiveness? And effectiveness is important in catalysts. You see catalysts as a powder that you sprinkle in a reactor, and that's fine. It shouldn't be a powder, because of course it will blow up, because it's a pressure drop across the reactor. It should be a pellet. The 2 chaps here have got 2 distinct types, and I've done that on purpose. So you've got one that might have a large surface area, and one that might have a very small surface area. But you've got different types. You've got built like a brick, you know what, over there. Brick outhouse might be the polite way of putting it, which is a steam forming catalyst. So it's built to last at flaming temperatures of the order of 600 to 1,000 degrees C. The other one, what is it? Is it a pellet or is it a rock? I can't remember. It's a pellet, so it's a circular disc. Yeah, circular disc tablet type thing. Okay, so that's probably, colour is it greenish? It's a low temperature shift catalyst, so it's due to operate, it's alright, I can see it. It's a low temperature shift catalyst, so it's due to operate about 250 to 350 degrees C. So completely different operating parameters in those 2 catalysts, completely different design catalysts. These 2, which are going to go around, and of course they will meet in the middle somewhere, so some lucky soul will end up with 4 on their lap. You've got, oh, I've maybe brought this steam for me. Have we got a ceramic in that one? Has that got a ceramic in it? Yeah, okay, so that's a honeycomb one then, yeah. That's a difference. So the explanation for built like a brick outhouse is actually this one. But that's a little wormy-like structure, and it's literally an extrudated catalyst. So it's completely different texture. One's very solid, one's very light, so it has a large internal surface area with a small internal surface area on the other one. So in other words, if we were to do the same reaction on those catalysts, it wouldn't happen, because we're opposing conditions, and also the effectiveness of those 2 catalysts is going to be very different, because the surface area and the porosity are going to be very different in those 2 catalysts. Ditto on yours, where you've got a honeycomb, and you've got a shift. You can see one's a solid pellet, the other one's a honeycomb. So it's known as a monolith type thing. It would be in your car if it was, for example, the catalytic converter. So if you cut one of so because you've got therefore a large surface area on the support. The other one is a solid pellet. So again, there's very different flow regimes for those 2 things. One where it may not need much absorption on the surface, the other may allow it, use it into it. And you've also got very different flow rates. So why I'm putting those there is just so you can see them and you can get the feeling of why is effectiveness important. Because one of the things I struggle with this bit is just, you're here, oh, I'm going to learn it. And that's fine. And you can learn it because the notes are actually now notes. So they're not necessarily the slides. I've highlighted bits of the slides. I've put up notes on the first couple of chapters already on Blackboard if you haven't seen them. So you can actually read through the notes and take it in. Here you've got the notes explaining everything. So I just want to get the concepts across. I'm not skipping anything. I'm allowing you to read it in your own time in the notes and then reinforce it with tutorials and questions to me during tutorials. We still have a tutorial at 3 till 4. So, start passing them around now, so you can start looking at them and passing them around. So the things that you're looking at, I leave it to your own imagination whether they actually are described by that model. Of course, you already know the answer. they're not. And they're very, very different. So you can't just assume when it says catalyst in that literature that you read for your design projects and so on and so forth, that the catalyst is a solid lump of something. Because those are examples of catalysts and catalyst support structures that are used in everything you know about and live today. So steam reforming and catalytic converters on a car, you're used to what comes out of it. So remember what we've done, we set it up almost like it's a plug flow reactor with a firm end, a closed bit at the end. There's no guarantee it would be closed in reality, but for here we're using it with a closed end. So we've got an element moving down where conversion is changing with distance moved, distance along the port. Then we put up some derivation, which is in the notes in front of you and should be self-explanatory, to end up with this funny little symbol, this funny little term down here called 2ks over RD times the length. And then we say, in a little minute, we're going to say that that little term and the square root symbol is M. And we're going to call it the Thiele modulus, ML. And we'll put up a graph showing what that is in a minute. So look at what you've got. You've got a term for a surface reaction, you've got a term for a radius, and you've got a diffusivity as defined by Fick's law, which I'm reliably informed that Tom covered as well in the very near past. And asked you whether you knew what he was talking about, and you all went, no, but you've already done it before, but now you've mentioned it again, and it's all done. So you've got, I only really want you to remember what that looks like. This thing is a definition of a particular thing. You need to look at that, and we'll talk about hypercosines and hypertangents in a min. But I just want to look at it, that term. We'll go on and I'll explain myself in a little more detail in a minute. So all that comes down to something which has got a hypercosine, ml minus x, which is the length minus the x moved along it, over ml times the concentration in the bulk. So the concentration at any point along that pore is concentration x, x distance along the pore of L length, okay? And then you've got that term, which we've pulled out as 2ks over RD. So without too much thought, you can look at that and say, what happens to M if we change the parameters within? So if the radius is large, the diffusivity is going to be low. Makes sense? Big hole, nothing stopping it going through it. Therefore, it'll be, that term will be large, that term will be small, that term will be much smaller than that is large, which will mean that that is generally getting to be a bigger number. If the surface reaction is slow, that tells you something else. So if that's slow and these terms are as we've just predicted, then we'll have a fairly effective catalyst. If the rate is fast, then you have to argue, why are we using the pore in the first place, and we want the catalyst on the outside. Okay? So why are we doing that? So you've got, this is how you've got to start to think. Just rationalize it, because it's not always it's not always intuitive. In other words, it's counterintuitive. You think about it, well, I actually need a large rate. Why is he saying I need a low rate? I need a large rate. So you've got to think about that slightly in the context of the pore. So look at the graph, the key graph. Always up on exam questions, this one. But a key graph anyway, because anybody who says effectiveness to you will say Thiele modulus, effectiveness ratio, and how does the concentration change down the pore? So first thing, look at the axis. Fractional conversion, fractional concentration down the pore. So concentration of A over the total that went in. So a hot 1 is good, 0 is bad. So good and bad catalyst, we covered it very quickly last time. We'll just put it up for your memory banks. Bad, and the one at the top, good. So ml of 0.5 is pretty much ideal for what you would say. Remember, we're never going to get 100% effective. No way. In reality. We can imagine it, but in reality we're not. So look at the curves, what the numbers are. So an ml of 10 means we've got a bad catalyst. In other words, we've got a reaction that's taking place here. Last time I asked, I think I remember asking, could that catalyst still be any good? And the answer is yes, because if it was a very fast reaction, you put everything on the outside and you wouldn't need to diffuse into it. A good example is the one that's the green big cylinder. There's a gentleman in the white shirt bang in the middle he's holding. So the one which has got the big hole in the middle that's built like a brick outhouse, yeah, that's the chunky one. You should have a oh, you've got the other two. Where's the chunky one got to? Where's the green catalyst with a hole like a Rashid ring in it? And if you don't know what a Rashid ring is now, shake it and it rattles. Yeah, yeah, don't shake it too much, don't get too carried away. You break the glass, it's that hard. Yeah. So, one sec. So, the one that's over there is actually got very low surface area because of its nature. It needs mechanical strength, it needs to go to high temperature, we need to light a flame and go from room temperature up to 1,000 degrees in a matter of moments. So consequently, it's not built to be an effective catalyst. It is an effective catalyst for the process that it's in, but it's not ml equals 0.5 up there. It's more like ml equals 10. The actual reaction takes place on the surface, and you don't need the pore. Now that is the bit that's confusing. Okay? So you're going to have to adjust your minds to that and read it in your own time. Yes, sir, question?
Honestly, it's confusing. Can you just briefly repeat?
Yeah, I will, and I've got a little graphic again. Go on.
Not the graphic, but the graphical method and how ML relates to effectiveness.
Okay, so the effectiveness of the catalyst is you want a low ml. So you want 0.5 as an effective catalyst. So that top line represents an effective catalyst. In other words, look at the concentration, fractional concentration, how much has got to the end of the pore. In other words, to 1 at this end. It's good that you asked the question, because you asked exactly the right question. Because I didn't explain myself well, because that's where you are. So 0 to 1. Let's assume that is now the end of the pore. If your catalyst is designed properly, you would want all your active ingredients equally set along the pore length. Therefore, if you do not get your concentration into the end of the pore, you're wasting all that money along the way. So if you put platinum in, which is very expensive, and you've dispersed it evenly over the length of the pore, and you get no concentration, in fact, no concentration after 20% in, why have you got that pore? What's it for? And you've wasted 80% of your active metal. At the price of platinum, that's a hell of a lot of money gone down the toilet. Okay? So the only time that that effectiveness at 20% could be useful to you is if your reaction is very fast, or in the case of steam reforming, has to go at high temperature, and you need a very strong catalyst to withstand mechanical strains that put on it. So in other words, there are circumstances where it would be a good catalyst, but most of the time it's not. So that is the confusing part. So understand the graph, I'll go through it again. So concentration down the pore, high number, high line, 0.5. So 0.5 line, look at that one. That says 92% effectively gets towards, the average is 92% about halfway down the pore. So you're getting most of your concentration of your reactant to the end of the pore. So it gets the opportunity to react at the active site. That's the key bit. In this one, most of your concentration is stuck. It never gets past 20% into the pore. So in a perfect world, with a porous catalyst that you've spent years designing and spending millions in R&D, and that gives you that answer, and you want that answer, that's a disaster and a whole waste of money, and lots of people get canned.
I have a question.
Yeah, where is that?
Hello,
front row, yes, hello.
When you're talking about pore, is it something inside the catalyst, or are you talking about something that we have made ourselves?
You never ask a question that's easy, but that's a yes and yes. So you're talking about a pore in the catalyst. So the pore is not. So I can drill a hole. So imagine now that I'm a chemist, okay? So I'm putting some ingredients together, and the way I do it is I want to make a structure of a certain type. So I use certain chemicals, and they then form a structure. I can do the same thing by putting a drill into the surface and drilling holes into it. I'm doing exactly the same thing in a chemical way to some materials that I make a catalyst to. I'm just drilling holes in and making holes, but I'm doing it in a chemical scientific way. So we make the holes in the catalyst. We can form the structures wherever the ceramic one is, which is the monolith. You can see you can form a structure which is a grid shape, like a graph paper, with massive holes in it. So you can make those things. So we're talking about pores inside the catalyst. So we've gone past the surface. We've gone down the wiggly bit that I've shown in the schematic, and that wiggly bit is the pore. We assume that pore is a straight line like an inkwell with a blank end. We then assume we want to know how does our concentration get through that pore. Does it get in? Doesn't it get in? Is the first question. To be effective, it's got to go all the way in. And then you hope that it's reacted on the way in or on the way out. The molecules are reacting on the way in or on the way out. If it's unaffected, it basically either doesn't get in the pore or just gets in a very little bit of that long pore. Does that help you with the question? So we make the pores, or you don't personally, someone So the confusion, which I did sort of on purpose, because everybody thinks they understand what I say and then they realise they don't the moment they get up and walk away. The steam reforming catalyst is a solid chunk of the most strongest alumina with nickel added at a ridiculously large percentage because it's wholly ineffective in its process of reaction. But it's massively effective if you go from room temperature to 1,000 degrees in a split second. It stands that strain, so it does its job. Okay? But it's not an effective catalyst in terms of a pore structure where you're trying to get from the beginning to the end. Okay? So there are two opposing thoughts. First thought is, I've got a catalyst that works. How come that's not effective? The answer is, of course it is. Define what you mean by effective. It's effective in mechanical strength, but not effective in the sense of getting a concentration all the way through the pores that are in it. So it's not designed to do the job that the beautiful monolith catalyst that you've got carrying around is doing, or the beautiful zeolite catalyst that I normally work on are there to design. So the way to remember it for an exam, and I'll put the schematic up, oh, this should actually help me. We've just explained that. That's a deal to remind me to do something. Okay. Yep. So we end up with an effective factor. I can come back to the slides. I'll show you what I mean with the slide in a minute. But we come on to effectiveness factor, and we've got the Thiele modulus, where we've got this on the Thiele modulus plotted against this effectiveness factor. And it gives a classic shape. There's a beautiful description of it, and there's lots of literature on Google, because I Googled it this morning just to have a quick look. There's some mathematical derivations which are for different shaped catalysts, but there are also a nice simple explanation of effectiveness. So you've got to think of now we've got a porous catalyst, which we want to have a porous catalyst. We want it to be as effective as it can be. Not the steam reforming catalyst, but a porous catalyst. So there are different, the normal standard line, which is shown there, is a derivation which we'll show in the notes and talk about again later on this afternoon. But allow for the fact that the dotted lines there are just because you might have more molecules produced or less molecules produced on your product from your reactant. So it's where there's a volume change. Let's focus in on the solid line, which is no volume change. If effectiveness, and in fact the straight line is just simply a gradient of 1 over the Thiele modulus. So you can see that most of the time it's a straight line, which is, for you as engineers is fantastic. You will notice also, of course, it's also a log-log plot, because it's the scales of 0.1 to 1 on one side and 0.1 through to 100 on the other side. So you're plotting the effectiveness versus the Thiele modulus, remembering that the Thiele modulus can be defined, and here's a slightly different derivation of it with the K incorporating the R factor as well, times the length, but it's got the diffusivity over the reaction rate. Key thing, therefore, is you want to make sure that the diffusivity is as quick as possible. So there is no resistance, and therefore you want, if there's no resistance, you effectively get a line which is 1 over ml, and I'll show you why that is in a sec. So, don't think I skipped anything on those other slides, but I might go back and refresh between now and 2 o'clock, just in case I did. But just for the sake of negligible diffusional resistance. In other words, now we're looking at that line, which is 0.5 versus the one, okay, which is 10. So ml. So nice and easy, just to remember it. I just like doing that. Don't get to do it often. Same graph, just so that it goes there, but not straight. to remember both of those. Same graph either side. Better drawn maybe on that side and maybe not on this side as well. But so we've got two conditions we want to look at. Just two. We want to look at an ineffective and an effective catalyst. Ineffective, bottom one. Effective, top one. Gentlemen asked a good question. They both asked good questions. Pores are in the structure. We want all our reactant to get to the end of the pore so that it gets to our active metal or our active site to do the reaction. If it doesn't, what's the point in having this beautiful catalyst you've just gone and wasted a lot of money and a lot of time. So you want an effective catalyst. Effective means concentration of your reactant gets all the way in the pore and has the opportunity to react all the way in and all the way out. That's what we want. So, for that then, the Thiele modulus, the effectiveness, which we're using the term E there, effectiveness is 1 if ml equals less than 0.5. All right, it approaches 1. It's not exactly 1. It can never really be 1, but it's as good as you're going to get, and it's the top line we're trying to describe. So looking at that, the same two symbols, and I'll put them really big so we can see them all. So 2Ks, K and Ks over R are equivalent. You can work that out yourself just on the surface area. You should be able to work out what the surface area of a cylinder is, etc., etc. So 2Ks over Rd is less than 0.5. If Ks is small, a reaction rate is large, the pore radius is large, and diffusion is large, then diffusivity is good, pore size is big, slow reaction rate, well, the reaction rate will just fix for the moment. These two things change dramatically what's going on there. So for that situation to exist, we have a large pore, we have no resistance to diffusion, end of story. So we're at that end of the graph. So that you just look at the graph now that you've got before. It should be highlighted. If not, you can highlight it yourself. So really you're at the beginning of the curve where it isn't proportional in this size to the size of the pellet. You get no resistance. If you've got no resistance, your rate of reaction is equal to the first order reaction. If A goes to B, your rate of reaction is the rate is equal to the rate constant times Ca as you would do in CRET. No, okay, so the question was, do all the conditions have to be fulfilled? That is the scenario that you would normally see, that the rate of reaction is probably slow-ish, because most chemical reactions are fairly slow, unless it's an oxidation, then it goes boom, so it's fairly fast, okay? So most reactions are fairly moderate pace, so that's just a statement for every chemical reaction that's an organic reaction, okay? There will be orders of magnitude, but not significant changes. So therefore, the two key parameters are the diffusivity. So if D is large, that means it's fast, and if the if D is therefore there is no resistance, so the number is small for D, so therefore you've got good diffusivity, then R must be large by automatic inference because you've got no problem with resistance. So the condition, that's just the condition it would be. Do they have to be applied? It's like everything. Yes and no. But mostly the rate is fixed to within a certain boundary, and then the R and the D link very closely together. So your key determinant is your radius. If your radius is large, you're likely not to have a diffusivity problem. You might have another problem, but we'll talk about that later. That comes into about interaction of the molecules then versus the active site. We'll talk about that in a different place. We'll talk about Knudsen and molecular diffusion a little bit later. They're all individual elements, but they need to come together. So we got the idea. You highlighted the right bit. So now let's look at the other one. Oh, didn't see your hand. Sorry, you're very polite. You didn't say anything as well. Sorry.
When you say saturation, that means the reaction rate of the reactants compared to that of when it's in the catalyst should be small, right?
Yeah. In other words, your reaction. I'm trying to say, don't focus on the reaction rate constant, okay? Because the reaction rate constant will be in certain boundaries. I know from experience it's within 3 orders of magnitude. So I'm not too worried about that. I would hope it was a bit faster and it was a bit slower because productivity would be better. But if you just fix that as a term and say, well, my rate constant is my rate constant, then the only term that really bothers you is the two terms of the diffusivity and the radius. If I make my radius really large, the chances are my diffusivity won't be a problem. by inference, if that interaction is low, my rate constant is going to be low. So it's all interconnected. Okay? The reason why I fix the rate constant is just it makes life a lot easier if you just fix that for a moment and think it doesn't change that much. Okay? But obviously, if you make your pore so big that there's no interaction, you're dropping your rate constant by default. You're automatically doing it. No reaction. Okay, let's go for the strong one, because the strong one is what everybody understands straight off the bat. So, big number. It's a log-log plot. We're down here. We've got a very ineffective catalyst, so there's a lot of resistance. And I'm hoping the next slide is going to tell us where it is. So now, literally, I can't get past this young man here. I'm stuck. What am I going to do? I want to get to that guy there because he's the active site, but I can't get near him. So the only thing I can do is get rid of a few chairs and make him the active site. Then I've got a chance of getting near him. So basically, all that straight line tells you, and it works for a ball, sphere, pellet, plate, for everything, is just reduce the length of the path. That's all it's saying. So everything on that line, which is here, that straight line, no matter what you've got, and you can see some of the shapes of the catalyst, that's why I passed them around. You can see solid cylinders, you can see little tablets, you can see spheres, you can see little worm-like structures. All of those fit on that graph. Pretty much, with the exception of the plate, which is just getting to the most effective part, all of them fit on a line which says, well, if I reduce the length of the flaming path, I'll improve the effectiveness of the catalyst. And I don't want to belittle what we all do and what I've done for many, many years, but that's it. The only control I've got over speeding something up, if I've got diffusion constraints, is I just make it smaller. Then the engineer comes along and says, Arthur, you can't just keep making it smaller, sunshine, because the moment you make it too small, we've got a pressure drop, and I'm going to blow your flaming catalyst out the end of the reactor. So that is it. It's no rocket science. Now then, the next thing that I want you to remember, because it's SF, it's in solid fluid systems and it's nothing to do with me, but when you're doing reactor design or design project, how many particles of the catalyst do you put across the bed to allow for no channeling reactor? So in other words, no bypassing. What is the number and what is the equation? Because you need just to always remember it, and I'll do it twice. It's nothing to do with this course, it's important for you to remember. So little d over big D equals 1/10, and little d over big D, that's where it all goes to pump. Little d, diameter of the particle, or the pellet, over big D, diameter of your reactor tube, is less than or equal to 1/10. So woe betide anybody in this room that designs a low temperature shift or a high temperature shift reactor, or a steam reforming tube that is the wrong diameter tube. So somebody came to me, one of our brightest students, who now currently works at a big multinational company, and she shall remain anonymous, designed a shift reactor that was 2 meters long and that diameter. Okay, who's got the catalyst? Somebody's rattling them. Have you got all of them, Young? What have you got? Okay, and we've got the discs, the tablets. Where are the tablets? Who said that? Oh, okay. Sit over. Thank you very much. What? Thank you. 1, 2, 3, 4, 5, 6, 7, 8. Okay, nearly 10. So any of you design a reactor, the bottle is the minimum diameter the reactor could be, not a pen. Not only that, a young person who was a first-class student decided to put 2 ton a minute through it. Really. I'm not an engineer, but that kind of doesn't sound like that will take 2 tons, and also that's the size of the catalyst, and you'd only get 3 pellets across there. So automatically, the key rule for you is little d over big D. Remember that big D is the diameter of the bloody reactor. It's not diffusivity, it's a diameter of the reactor. But that just gives you an example that you can see. I know that I need 10 of those things, minimum, better 20, to stop channeling. You know what channeling is? Just bypassing through. And that's from solid fluid systems. So for all the MSc students in the class who think they haven't done that, that's the only bit solid fluid systems. And what else? Oh yeah, voidage, which is typically 0.5, 0.4 to 0.5. Those are the two bits of key information you need to design the amount of catalyst that you need in your reactor. After that, you need to know the rate constants, and it gets a little bit more complicated, but that's it. So if you know that you've designed a tube and it's the wrong diameter, because you've seen Arthur's lectures, and there are some pictures in the notes a little bit later, we'll come on to that, you can automatically tell my reactor has got to be bigger than 10 centimetre, or maybe more, maybe less. So it's got to be that diameter, minimum. I'm a man, I always get distances wrong. Don't know what that is. Steady. Know your level. And we've hit the bottom. Right, okay. So, get the idea. We've got a nice simple plot. What are you plotting? Effectiveness against telemodulus. Okay, so ml on the bottom, effectiveness on that side. You're literally left with a very blunt tool, which is 1 over ml. Change the length of the particle. Make it smaller. You can see what would happen in a Schiff reactor. I make the particle 1/10 of the size there. I end up with near dust. The near dust is going to blow out at the end of the reactor. It's going to contaminate everything. It's going to be a disaster. Stop giggling. I can see you. So in effect, what we've done with the two scenarios, that's it. That summarizes the lecture. It summarizes the whole thing, but it's getting your head around that plot, which is here, understanding that that's effective. That is not. Why? Because the concentration of the reactant does not get into the structure that you've designed for it to do the job. You end up with those two equations. I am now modeling my reactor based on, I've got the assumption that it is surface reaction limiting. Because I'm telling you 75% of the time it is. I'm going to try to hope that none of my products or my reactants are absorbed on it. And then the last thing is, I'm going to hope that my limitation on diffusion is not present. And there are ways, and I will tell you how we do that in a lab, to determine whether we've got diffusion limitation or mass transport limitation. And it's dead simple, and it all links to the Arrhenius equation. So it's all stuff you've done, it's all stuff you just need to pull together from different points. This is your summation. Obviously, if you've got diffusion restrictions, you're going to have this complicated thing on the bottom where you've got basically 1 over ml. Which is this one. But look what it looks like. Rate constant times concentration with the diffusivity term. Bulk density of the catalyst, surface area of the catalyst, rate constant of the surface reaction, times the concentration that you've got at that point in the pore, times 1 over ml. But the top one is approximating to your first year kinetics, your second year CRE2, and third year CRE3. There is no resistance, so you're going to say, well, I've got this catalyst. I've got a bulk density, which means it's about half of what I think it is, so I need twice as much catalyst. I've got a surface area, which is the size of a few football pitches, so that's fantastic. I've got a great reactive surface area, and I've got no diffusion constraints, so my rate of reaction is going to be proportional to my concentration in. That's it. So although it looks complicated, the concepts, I think, is what you struggle with. The actual result is we've got that equation without that last term, or with that last term, and that's it. Can't say it any other way. In the end, the revelation comes usually to my fourth-year dissertation students when they all study reactors and go, oh, that's what that course was about, which is not what I want. I want to achieve that now, but I have to struggle to get through the concept. So hopefully you've now got it. Top one, good. Bottom one, bad. If you get the bottom one, what do? Your immediate answer in an examination question or in class when I ask it this afternoon is, we just divide the length. We get it smaller. We want to make the particle smaller, so we get this as low as we can so it becomes the equation at the top. And when we think of it, because you are engineers and I am a chemist, you think of it in terms of a log scale. So it's always change it by an order of magnitude. Always. You automatically try to change something by a factor of 10 because it's a dramatic change. Noticed on the concentrations, we were trying to change it by doubling and quadrupling. It was rare that we did it by tenfold. Okay? just see where we're at with that. So the last bit, for the last 3 minutes, and then I'll stop for once on time for poor Tom to give him a proper lecture. I'm assuming now we've got that concept. We've done all the basic theory which is built on this very nice straight pore. But it's not true. So we have an effective false teeth back in place. An effective diffusivity. And the effective diffusivity is going to be the pellet porosity times divided by the tortuosity, in effect. So times the diffusivity. So the original diffusivity is got to be divided by the tortuosity. And what do we mean by that? That's an example of a real pore. If you just simply looked at that and drew a straight line, you'd say actually the distance that the molecule travels, because it's a sine wave of course, is going to be twice that of the actual length. So in effect, your effective diffusivity is going to be half of what you predicted it to be. So I said we'd touch upon diffusion, and I don't want your brains to explode. So we'll touch upon diffusion now, and we'll talk about molecular diffusion and Knudsen and configurational diffusion, which are in things called zeolites. So the stuff that you're handling is a formed catalyst. Those of you who looked at the wormy-like structure, that's an extrudate. So it's been pushed through something, and out the end, like sausage meat or mincemeat, comes out in exactly the same form. And it has a different kind of structure to that alumina that we just saw for the steam reforming catalyst. So the steam reforming catalyst has virtually no surface area, whereas the zeolite has massive surface area, and obviously the zeolite's got lots of holes in it, so therefore it's got lots of porosity, and those pores tend to go around a bit, and they tend to be sinusoidal, so they tend to give you an effective diffusivity that's half of what you predicted it would be. But Knudsen diffusion simply means the molecule is now the size, or is approaching the size of the channel. So the molecule actually wants to interact with the side of the channel, and that is good. Why? That is good because our active sites are on the wall, so we want the interaction. The molecular diffusion means two molecules bounce off one another. And if they bounce off one another and react, why do they want to react? Why do you need the catalyst? You don't need the catalyst because you could have done it in a tube, if that was the case. So always when we're talking about catalytic reaction engineering, we're looking at somewhere between those and moving towards configurational diffusion. And I'll tell you now, configurational diffusion is not very well explained even after 50 years of them talking about it. Yes,
Sir, I just want to ask, what are zeolites exactly? Are they minerals added to catalysts?
Okay, so we've got a whole set of lectures on that, and you'll all glaze over on one of them, I can tell you now, because I start getting carried away because it's my specialist topic, okay? So I have to contain myself, so you can control me when I do that. So zeolites are just silica aluminum matrices. So that's ceramic that's just been going around. Imagine that now is a set of bonds, and they're not quite as well formed as that ceramic, and that's a zeolite catalyst. It's basically a network of channels of molecular dimensions made of silica and aluminum.
So it's a catalyst by
It's
itself.
a catalyst by itself as well as a support for active ingredients. So it can react in its own right, but it can also be a support for metals, which then allow you to do different kinds of reactions.
So you can add metals to allow the two catalysts.
Yeah, that's a whole field in its own way, but not for us. Not for us. Too much info. You want to imagine them as magic dust. It's fine.
Could you repeat the difference between molecular and crystal?
Certainly, in molecular diffusion, two molecules, you basically got an open space and two molecules can interact with another molecule. So we've got an open tube, we've got lots of molecules in it, and it's very wide, this tube. So what's the molecule going to see? It's going to see another molecule. I don't know. Click the molecule, it might interact with enough energy to cause a reaction. So molecular diffusion is where we're talking about a chain of molecules moving through a very open space. Knudsen diffusion is where the molecule is of the size of the pore. So that hole in the table is about the size of the bottle. So now the molecule is wanting to interact with the walls of the hole it's coming into. Okay. Whereas this one is lots of space, so it doesn't have to. Right? Configurational is where it gets so tight that you're now getting to the point where even the molecule can't get in the pore. And that means it's not very effective and not much use to you. Because why have you got the pore if you can't get in? Okay? So we're on the boundary of that one and that one, moving to where some wonderful things that you do, such as nitrogen and oxygen separation from air, pressure swing absorption of CO2, are all done on a molecular scale that is virtually the size of the nitrogen diatom and the oxygen diatom and CO2 molecules. And that's why my stuff is very interesting to engineers and the process. But you're not really interested in my stuff. You're really interested in me not messing up your reactor. That's what you're really interested in. And that's where this course is coming from. So, teleMOS and particle diameter I've covered. Oh, we're not going to get onto that because we're going to be here all day, so we'll cover that this afternoon. So, if you didn't get it, read the notes between now. I know you've got Tom next. If you get the chance, read the notes over lunch. Obviously, I recognise that's a difficult ask. And we'll cover it again this afternoon. Remember, there's a lecture in here for the next 3 weeks at 2 o'clock. We've got a 1-hour tutorial at 3 till 4 in James Chadwick. How successful that will be for the next 10 minutes, I do not know, but we will try anyway. Okay. Thanks very much, everyone. Have a break before Tom gets here. Okay. Oh, okay. I only had actually 4 slides. I could have finished that. Never mind. So we have got time for questions today, which is good. Let's go away from the microphone. So that we don't... So why do we have the course? If we've just got a solid surface, that's my surface area. It's now aiming to measure. We've got lots more surface area. So we put the holes in to make more surface area to give you a better reaction. However, if we can put the holes in, we affect the diffusion so badly that it doesn't go in anymore. That's the purpose of today's lecture. That's it. You've got it in mind. Okay. The rest is all talk and you don't need to worry about it. Yeah. Oh yeah, this is the particle diameter. And that's the diameter that you... Yes, Simon, I need a little...